Another easy way to find them is there's only 50, if you're talking about US victims, there's only 15,000 banks and credit unions in the US. And each one of those only has a handful of login pages. So it's fairly trivial to go out, scrape them all, and to gather a collection of those. So again, not really much protection. And then of course, if you're a bad guy, you probably know a lot of the sites that you want passwords for, whether it's Facebook or MySpace or Twitter or whatever it happens to be, and you know the login page. So again, you can just pre-compute those. And then if you really get desperate, Alexa keeps tabs of popular sites, and you can just grab those. So it's really easy to decrypt these. You can do something like basically create a rainbow table out of all these common sources, and then you've basically got all the keys to decrypt all the passwords. So for the bad guys, it's fairly straightforward. So the moral of the story for IE7 is it's not looking good. But maybe there's help. Or there's not. So nobody really does a good job with this. Actually, Michael and I looked at a bunch of different applications, AIM and Mozilla Firefox, basically everything, try to write password recovery tools for them, and you can write a password recovery tool for pretty much everything. There's really not much that will help protect you if you're storing passwords in any sort of application-specific, remember my password thing. They're pretty much all recoverable in some more or less trivial way, IE7 included. Firefox is probably the strongest of those, since you actually have to enter a password first, but even then, if you've already entered your password, the bad guy can sort of steal that too. So, moral of the story, don't get compromised. Kind of helps from getting your password stolen. Don't save passwords of value, and if you run a site that does have a login form, there's some little tricks you can do to basically tell IE, don't save these passwords. So the last one, we have, there's a Trojan called LACMA, and what it does, same typical Trojan where basically they steal login credentials, and they steal all sorts of other pieces of data. And one of the things they steal is cookies. I love cookies. So when they upload the cookies, they do it in a kind of strange way where they don't necessarily sanitize the data. So the user gets infected, the malware steals the cookie value, and then it uploads to the command and control site. And when it does it, it just uploads it with whatever file name that happened to be. And if you're emulating the Trojan with your own code, you can specify that to be anything you want, like say another PHP file. So you can just upload your own PHP script to the bad guy's site simply by using this. It's literally just an arbitrary file upload vulnerability. So I'm going to turn it back over to NHL for one last demo.
Sorry, this one isn't funny, but watch anyway because I think it's cool. I was just trying to find a way to fit this demo into the presentation, which is why it's kind of not funny. But it's based on the LACMA rootkit that it installs. Just imagine that you're an incident responder or you're a malware reverse engineer and you encounter a machine that is infected with LACMA or any type of rootkit that places hooks into the system service dispatch table. So first, what you might want to find out is what functions exactly are hooked in the SSDT. And then you might want to go and recover the kernel module that's running in order to inspect it with IDA or something. So it's a really cool plugin that I wrote for Volatility that automates all of those tasks. So I've already, behind the scenes, taken a memory dump of a machine infected with LACMA. And then I'm just using the SSDT plugin from Volatility. It's by Brendan Dolan Gavitt. It's an awesome plugin. And what it does by default is just prints all of the entries in the SSDT and the owning module and the address of where the SSDT function points. And it does that for all 4 of the SSDTs. The first one, all of the entries should be legitimately pointing inside NTOS kernel. For the second table, they should all be pointing inside the Win32K. And for the third and the fourth, it's a little arbitrary because those are not set by default. So I'm going to use Brendan Dolan Gavitt's SSDT script, and on the command line just set a filter with egrep so that I ignore anything that points inside NTOS kernel and anything that points inside Win32K. And what I end up with is 4 functions down here that point inside a module named landman drv.sys, int enumerate value key for hiding registry entries, int open process for hiding processes, int query directory file for hiding files, and then int query system information. So, like I said, that's the first step. We wanted to know which SSDT functions that this rootkit hooks. The next step would be to dump the module and then look through it with IDA to try and maybe figure out what processes it's hiding, what registry keys it's hiding, what files it's hiding. So I automated that task a little bit, a plugin called SSDTEX. And you can see that blue screen flash by really quickly. And that was actually IDA's command line program that I automated to process the landman drv.sys after having dumped it from memory, after having identified that the 4 hooked SSDT entries point inside that module. So furthermore, after automating the creation of an IDB, it does a little bit more automation and goes as far as actually labeling the functions in the IDB according to which SSDT functions that it hooks. So just in one easy step, we found out which SSDT functions were hooked, dumped the owning module, created an IDB of it, and then named the function so I know exactly where to look in the IDB when I start reverse engineering it.